Hello everyone, this is lecture 8 of course PE 645. In the previous lectures, we have covered multiple handcrafted features, techniques such as first order features and second order features, including GLCM and GLRM, and we applied that to a machine learning model after selecting the best model and the best scaling technique according to a set of performance metrics. We reported accuracy, precision, recall, and so on. And all of that follows the workflow of the artificial intelligence. We compared them between the first order and second order and higher order features according to the definition of each of them and the purpose. So in this lecture, we are going to continue how to extract more features. But for today, we are going to cover a different approach called local binary pattern. And LBP or local binary pattern is a texture descriptor which is used in image processing for feature extraction. And LBP describes the local structure of an image in a way that's invariant to changes in illumination. So if you have a set of images which is taken under different types of illumination, or a certain image has different types of illumination, then you can use LBP to describe your image and the local structure of that image based on the appearance features. This technique was introduced in the 1996 by Ujala et al. And since then, this technique is applied in various domains such as face detection and picture classification. And LBP works simply by comparing the intensity of a central pixel in a small neighborhood, let's say 3 by 3. So the central pixel will be this one, with the intensity of its surrounding or neighboring pixels. So we are comparing that pixel with the surrounding pixels. Each pixel in the neighborhood is assigned a binary value, whether it's 0 or 1. And this is based on whether its intensity is greater than or less than the intensity of the central pixel. And the central pixel here is like a threshold. So simply if we have a value here by 100 and a value here by 200 and another value here by 50, then we are checking if this value is greater than the threshold or not. So this is above the threshold, which is a central pixel, and is below the threshold, which is a central pixel. Then, using these binary values, we can construct a histogram of the texture distribution within an image, or also we can get other features such as GLCM or GLRM features. So the idea behind LBP is simple. We have a center pixel and we are comparing the neighborhood with that threshold or center pixel, and we are giving new binary values, and based on these binary values we are concatenating them again to a new number. For example, let's assume that we got here 10111011. So based on these binary values, we are converting them to another numeric value, which will be a new value that will be set here. So you can say that we are changing the central pixel or the threshold here with another value. Then we are repeating that process on all of the pixels. So here we have an image. We are converting it to another numeric matrix. This matrix, or each pixel in this matrix, will be like a relationship between the central pixel or the threshold and the neighbors. And using that manner, we are constructing an image which is invariant to the changes in illumination. So how do we calculate it? The first step is you will choose a pixel in the image, let's say that pixel in that matrix, and then you define the size of the kernel or the size of the neighborhood pixels, let's say 3 by 3. So you will get a surrounding pixels like that, and then these neighboring pixels will be like a circular or rectangular region. You can whether depend on the annotation of the rectangular or circular region around it, but the aim in both of them is to get the center pixel and the neighbors based on the size of the kernel or the size of the neighboring pixels. A second step is to take the threshold, which will be your current pixel, which is 40 in this case, and then compare each neighbor with a pixel. If the neighbor pixel is above the threshold, which is the center pixel, replace that value by 1. Otherwise, replace it by 0. So in our example here, we have 21 and 22 and 18, or the first row is less than 40, so we are setting here zeros. 23 is less than 40, then 0 is put here. The same for 21 here. But for 55, it's above 40, so we put here 1. The same for 41 is above 40 or equals, then it's 1 here. And for 80 and for 28, it's 0. So you have an original neighboring matrix and a threshold, and you are getting a binary matrix. After that, you will need to combine that binary matrix into a numeric value. How we can do that? Simply by multiplying it by the powers. So you are multiplying each pixel here by 2 to the power of a value, according in which way or in which cell you are starting, and if you are moving clockwise or counterclockwise. To make it simple, let's say we are starting from this position and we are moving counterclockwise. Then simply create another matrix similar to the original or the obtained matrix in size and fill that matrix with 2 to the power of a counter starting from 0. So here it will be 2 raised to the power of 0. And we are moving counterclockwise. Then the next value here will be 2 to the power of 1. Here 2 to the power of 2. The same here, you are increasing until you complete all of the cell, and you will end here by 2 to the power of 7. Multiply the corresponding pixels. 0 multiplied by 2 to the power of 0, 0 to the power of 1, 1 multiplied by 2 to the power of 2, and the same for others. Sum all of that together, then you will obtain a final value of 12. After completing that, you will change the original threshold by the new value, which is 12 here. Next, you will repeat these steps for each pixel in the image to obtain the binary code for each pixel and the corresponding decimal value. Let's get another example here. We have that matrix with that threshold. And here, let's assume we are using 3 by 3 matrix. Then compare. So simply, these pixels are above 18. So we will fill here them by 1. And these pixels are below 18. So here by zeros. We said, let's assume we are starting here and moving counterclockwise. So we are going to fill or create another matrix filled with 2 to the power of a counter starting from 0, and we are calling that matrix as the kernel. So here 2 to the power of 0, the same for others until you reach 2 to the power of 7. Multiply each corresponding pixels, sum all of that together, you will obtain 143. So you are going to replace that value in the original matrix by 143. You will do the same for all of the pixels. So now you will obtain a new matrix different than the original matrix, but they are similar in the size or the shape, width and the height. So the idea here is simple. You have an original image or an original matrix, then you are going to create a new image or create a new matrix, same in shape but different in values, and the new created matrix will be invariant to the illumination. It changes. But you may wonder now why we are creating a new image, not getting features. The situation here is simple. Local binary pattern creates a new image with the feature of invariant of the changes of the illumination. And the benefit now is that you can use that new created image to extract features from it. How? Simple. You have an image, you applied LBP, local binary pattern, to that image, you created a new matrix, then you can use that matrix to extract any other features such as first order features, GLCM features, and so on. So instead of applying these handcrafted features on the original image, now you are applying it to the LBP matrix. So the benefit is doubled here. you are extracting handcrafted features that you know the meaning behind each of them, and also these features will be invariant to the changes of the illumination. So how to create the LBB matrix programmatically? Let's start by creating the LBB kernel. And the LBB kernel, as we mentioned, is the kernel that includes 2 raised to the power of a counter starting from 0, because we will use that kernel later after obtaining the binary value to obtain after that the decimal number. So the first point here is how to create the LBB kernel. If you notice in our example from a while, we mentioned that we will start from that corner and move counterclockwise. But what if we have different distances or different theta values or different directions, clockwise or counterclockwise? Then we need something to generate the LBB kernel based on these 3 values or these 3 parameters automatically, as we don't need to define them manually. We don't need to define different matrices, and we say if the distance is like that and theta is like that and we are moving counterclockwise, then use that one, otherwise use that one, or use that one, or use that one based on the conditions. We don't need to do that. We need to make it in an automatic manner. So the input to the function that will create the LBB kernel will be the distance, theta, and direction. Distance means whether you need a 3 by 3 matrix or 5 by 5 matrix and so on. You are increasing the distance. And we will know later the effect of the distance on the output image. And theta here will define at which cell we are going to start, starting from 0 here. So if we define 45, then the target cell or the starting cell will be that one. And if we define it 90, then the starting cell will be here. So in our example here, if theta is 180, then it should start from here. And the direction is clockwise or counterclockwise. So if you are moving clockwise, then the increment of the cells will be to the direction, and if counterclockwise will be the direction. And to make the situation generic, we will ignore these values for a while, which are the required parameters, and we will construct a pattern or a template for all of the parameters, and then we will update and modify this created template or kernel based on the distance, theta, and direction. So first, we will create the default coordinates and get the unique coordinates of them. How? We will start the first row and fill the coordinates 0, 0, 1, 0, and 2, 0. Then start by the last column 2, 0, to 1, to 2. Then followed by the last row 2, 2, 1, 2, 0, 2. And then the first column 0, 2, 0, 1, and 0, 0. Now we listed all of the coordinates following that pattern. Then we will filter them to avoid any repetition, because there are repetition here, repetition here, repetition here, so only will find the filtered coordinates without any repetition. After that, we will rotate the coordinates based on the given theta parameter. We have the given coordinates, and we need to obtain the shifted coordinates so that we obtain the correct starting cell. How we can do that? Simply using mathematics. We have number of elements equal to 8 multiplied by the distance. So 8 multiplied by 1 will be 8. Then find gamma, which will be 360 divided by the number of elements. And in our case here, we have 45. Then check the shift. Theta minus 135 divided by gamma. And then floor the value if there are any decimal points. 135 is put here because if you notice, we started from the top row, from that cell, and that angle here is 135. So this will be our reference. And gamma here is the difference angle between the different cells. And theta is required. So 180 minus 135 divided by 45, floor this value will be 1. So start at index 1 from the coordinates. So we will start from here. Then we will continue until we reach the end. What about the beginning coordinates? Simply take all of them, append them or concatenate them at the end. So 1 0 until you reach 0 1, which is here, and the remaining will be concatenated here 0 and 0. So this will be our flow to fill the LBB matrix. We need to fill the matrix based on these coordinates. First, we will be manipulating the coordinates following the NumPy matrix, as these shifted coordinates and the NumPy matrix will be starting from y then x, not x and y, as we are dealing with traditional mathematics. So we will start by 1 and 0, y and x, where the first part here in NumPy reflects the row and here reflects the column. So we will fill here 2 raised to the power of the counter starting from 0, so it will be 2 raised to the power of 0. Then 2 and 0, which is here, will be filled with 2 raised to the power of 1. Then 2 1 will be here, and we will do the same until we fill the complete matrix, which is here, from 2 to the power of 0 until 2 to the power of 7. And it's worth noting that depending on the rotation, whether we are dealing with clockwise or counterclockwise, we will do a simple manipulation here. So if you are dealing with counterclockwise, then you are doing perfectly, and here is a final matrix because we are following the counterclockwise loop. And if you are dealing with clockwise, then you will do a simple thing, which is keeping the first coordinate as it is and reverse the order of all of the other coordinates, and we will show how to do that programmatically. After that, based on clockwise or counterclockwise, you will obtain the final kernel or the LBB kernel, which is here, starting from angle 180, which is here, and moving counterclockwise in the direction with a distance of 1 means 3 by 3 LBB kernel matrix. So simply in the helper files, we have created a function called build LBB kernel that accepts the 3 parameters, distance theta and is clockwise, false or true. And this function should return the kernel. After that, inside this function, we made a check. If the distance is below 1, then we will return with an error that the distance should be 1 or greater than 1. Then we created the number of elements, 8 multiplied by the distance. Then we created an angle variable, which is the difference between consecutive elements, which is 360 divided by the number of elements. Then we checked if the angle is within 0 and 360. Other than that, it will raise an error. And if theta is not a multiple of the angle, then it will raise another error. After that, we created a kernel with a specific size equal to 2n plus 1 or 2 multiplied by distance plus 1, which is here filled with zeros. Then we created the coordinates list and we will start to fill it. The rest we appended from top to the bottom and the left to the right. And these are the coordinates without any filtration. After that, we will remove any repeated coordinates by looping from the end to the start and check if any consecutive coordinates are similar. If so, then we will pop or remove the current coordinate if it's a duplicate. Also, we will check if the last one is similar to the first one, then we will also remove it. Now, we removed the repeated coordinates. Now we need to get the shift using the formula that we defined in the slides, theta minus 135 divided by the angle. We got theta shift, then apply the theta shift to get the coordinates. If we are applying clockwise, then we will get the first coordinate and reverse the order of other coordinates except the first one. Get all of that. Now we have the coordinates, whether you are dealing with counterclockwise or clockwise. Now we will start to fill the kernel by values to raise to the power of counter starting from 0. Now we are looping according to the coordinates and filling the kernel. Then we performed that step to match the expected orientation. And simply here, because the coordinates of the traditional math defined in the lecture is different than the NumPy coordinates, so simply we apply the transpose here programmatically so that we can match the coordinates or match the kernels between the NumPy definition of the coordinates and the traditional mathematics. In all ways, we got the kernel. Now go to code 26 local binary pattern kernel creation example. We imported the helper file, defined distance, clockwise, and theta, passed them to the function and got the corresponding kernel, and then printed them on the command window. After executing the code for different parameters for distance, theta, and clockwise, you will get the corresponding outputs. For example, for angle 315 with a distance of 1 and clockwise false, you will start from here. Clockwise false means counterclockwise, then you will move to the direction. So you started here from 1, 2, 4, and so on until we reached the last element. Another example, start from angle 90, which is here, counterclockwise, like that. And these are other examples when clockwise is true. This means we will move to the direction. Let's say we are dealing with 225, which is this angle, and clockwise, then you move to the direction until you reach that value. When you increase the distance, this means you need a bigger kernel, and we mentioned that we are going to emphasize the importance of changing the distances and comparing between them. So for example, 135 means that you're starting from the point which is here, clockwise, then you move to the direction, then you are starting from 1, 2, 4, 8, and so on until you reach that value. The second thing that we need to cover after creating the LBB matrix is how to handle the boundary cells. Simply, if you have a boundary cell like here, 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 or here, how can we get the different neighbors? Simply, you are applying padding around the image with a specified distance. So if the distance is 1, then you will add a layer of zeros around the image. And if you have a distance of 2, then you will add a second layer and so on. So based on the specified distance, you will add number of layers equal to the distance. And these layers will be filled with zeros. So when you compare between the current pixel or the threshold and the neighbors, in most cases, or you will find that these values is lower than the threshold, and the corresponding binary value also will be zeros. So you didn't make any big modifications or alternations to the original image. Now we need to combine all of the steps together so that we can give the code or give the function an image or a matrix and get the corresponding LBB. So here we start by defining the 3 parameters as we did, the distance, theta, and the clockwise or counterclockwise. Then create the size of the kernel, which will be called window size, based on 2 multiplied by distance plus 1. So if you have a distance of 1, then you will get for sure a kernel 3 by 3. And if you have distance by 2, then you will get a kernel 5 by 5. Then get the center x and center y of the kernel by dividing it by 2 and flooring the values. You will get the coordinates of the center x and center y. Then create an empty matrix called LBB matrix to store the computed LBB values, and this matrix has a shape similar to the input matrix. Then generate the LBB kernel as we did from a couple of slides, and we discussed how to do that. Then pad the input image with zeros, and the padding here, or the number of layers that will be padded, equal to the distance using the function np.pad. Now we have prepared everything to start looping on each pixel in the input matrix, and let's assume that matrix is called A. Loop on each pixel starting from 17 and moving to the right row by row until you reach 10 here, and do these steps. First, extract the region of interest, which will be 3 by 3 in that case, around the threshold or the current pixel. Then compare the threshold or compare the neighboring pixels with the threshold. If it's higher than the threshold, then replace or give a value of 1 or a binary value of 1. If it's lower than the threshold, then give a value of 0. After that, multiply the obtained binary matrix by the LBB generated kernel. You will get a final value, which will be a numeric value. Replace or set that value to the new LBP matrix, which will be named here LBP matrix. So if you have coordinates 0 and 0 in the input padded matrix with 17, then 0 and 0 in the LBP matrix here will be the new generated or the new calculated value here. To know how to do that programmatically, go to code 27 local binary pattern example. Here we imported matplotlib for plotting and visualization, NumPy for numerical operations, and imported the helper file. And inside that helper file, we created a new function called local binary pattern 2D that accepts the input matrix, the 3 parameters, and if we wish to normalize or not. And the output from that will be the local binary pattern matrix. And for sure, that function will be using the other created function, which is called build LBP kernel. First, we made a set of checks regarding the distance and theta to validate the given or the input values are correct. First, the distance must be greater than 0 and less than half of the matrix dimension. And second, theta must be between 0 and 360, and theta must be a multiple of 45 degrees. Also, we can make this value more generic so that it can accept different distances and thetas. So based on theta, we'll get the number of elements and divide 360 by the number of elements. In case if you have different distances, then the angle will change from 45 to another value. Then instead of 45, we will replace it by the angle here, and we will format that and insert, instead of 45 here, we will insert the value of angle. So when the error is raised, it will say theta must be a multiple of a certain value here, degrees. Here we created a variable called window size, and based on that we will get center X and center Y, that we will get the benefit of it later after a second. Created the kernel by calling the build LBP kernel function, giving the 3 parameters and obtaining the kernel matrix. Created an empty matrix to store the computed LBP values and padded the image with a constant value of 0 based on the distance. Then we looped on each pixel in the original matrix starting from distance, because simply the dimension of the padded matrix would be different than the matrix. So we are starting from distance because we need the values of the matrix themselves, not the zeros inside the padded image or the padded matrix. Then we extracted the region of interest, which will be in size 3 by 3 if distance is 1 and 5 by 5 if distance is 2, and so on. Then we compared between the center pixel of the region and the rest of the region. Now we have a binary mask. Based on that binary mask, we will get the correspondence from the kernel, which is filled here, that carries the values of 2 raised to the power of a counter starting from 0 until you reach the end, and sum all of that together and fill the LBP matrix with that weighted kernel value. After that, we checked if the normalization is applied. Then we will apply min-max normalization. The reason here is we have different ranges. So to restrict the ranges between the minimum and maximum and then convert it to the range of 0 to 255, then we will apply min-max scaling by simply finding the minimum and maximum value, apply min-max scaling, and then multiply by 255 to get the LBP matrix, convert it to unsigned integer to be represented as an image, then return it that matrix. In the example here, we defined a matrix, then we converted it to unsigned integer matrix using numpy.array, defined distance is clockwise, theta and normalization should be applied, especially if you are dealing with images, called the function, passed the different parameters here, got the LBP matrix, then we printed both of them together on the command window and created a figure here with 2 subplots, the original matrix and the LBP matrix. And when you execute the code, you will find the following output. This is the original matrix, and this is the corresponding LBP matrix, and this is the corresponding figure with the 2 subplots, the original matrix and LBP matrix. You may note that there is no interpretation of the image or the matrix in that case here and here, but you will find a difference when you are dealing with a big image, as we are going to see in this example. So here we need to apply LBB on the cropped image with the specified parameters, theta, distance, and is clockwise or not. So go to script 28, local binary pattern for 2D. We import the libraries and the helper file, defined the patterns for the image and the segmentation mask. It checked that both of them exist, then read both of them in the grayscale format, got the ROI, got the cropped image. It checked that the cropped image is not empty. Then we call the same function local binary pattern 2D as it's accepting a matrix, whether it's a small matrix or an image, passing the parameters here. Distance is 1, is clockwise false, theta is 135, and apply normalization for sure. And this will obtain the LBB matrix that we later plotted it alongside the original image. Also, we calculated the histogram for the original image and the LBB matrix. Also, we got the percentiles for both the normal histogram for the image and the histogram for the LBB or the LBB matrix, and printed both of them. And also we plotted the histograms for the image and LBB matrix. After executing the code for distance 1, counterclockwise and theta 135 and apply normalization, you will get the following LBB image, which is here from the original image. The background is ignored, which is black converted to white. And if you notice here, the LBB could capture the fine-grained details from the lever, which will not be captured by the human eye. For example, this region, which is here, and the details here, which was here. And also, if you notice that the original image had a histogram around 100 and 150, which is now became invariant to the intensity and distributed all over the pixel values. Also, if you notice that the percentiles is now distributed compared to the original percentiles of the image or the cropped ROI. And now we are going to increase the distance from 1 to 4 to capture what is the benefit of changing the distances. So this is distance 1, and now we increase the distance from 1 to 2, and from 2 to 3, and from 3 to 4. If you notice here that global patterns are emphasized by increasing the distance. If we combine all of them together in a one plot, here, distance 1, distance 2, distance 3, distance 4, now we can understand the differences. So by increasing the distance parameter, we are shifting the focus from capturing the fine-grained details to make it global patterns. So now here, the fine-grained details disappears and the global patterns in the lever appear. Also, if you change the angle, the global patterns change. There's angle 135, there's angle 180, and there's angle 315. Comparing them together, we are capturing different global patterns. And you may wonder which angle or which distance are we going to capture. Simply, you have two approaches. The first, you have multiple approaches, including try and error. You can try different distances and different angles randomly and check which is best, or apply optimization technique to check the most suitable of them, or depending on what is your target. You need the fine-grained details, then you are focusing on low distances, or you need global patterns, then you are increasing the distances. And regarding the angle, you can check which angle can produce the most global patterns. For example, here in 315 and in 180, you may say that 315 captures more global patterns than the other one. Because if you notice here, there is a pattern which is captured here, there is another pattern here which is captured here, and the same here, which is captured here. Or you may say, I may extract different features from different distances and from different thetas and combine all of that together inside my features file and apply the machine learning on all of that. This is another idea. So you have different opinions and different alternatives of how to capture the best distance and theta, or how to capture features from local binary pattern. Local binary pattern has different advantages and disadvantages. Some of the advantages, it's robust to illumination variations. As we mentioned, it captures texture information in images with varying lighting conditions, and this will make it useful for applications such as object detection. It's computationally efficient, and it's invariant to rotation and scale, as we saw in the previous couple of examples, and it's highly discriminative, and it has proven to be highly effective for texture analysis. But on the other hand, it has different disadvantages, such as it's sensitive to noise. So if you have a noise or high amount of noise in your image, then it may lead it to be inaccurate. As you are comparing between the threshold and the neighboring pixel, then the noise can mislead the binary masks and the corresponding decimal values. It has limitation to local texture information, and it has difficulty in distinguishing between the textures that differ in rotational patterns. And finally, it has a grayscale limitation, as it cannot be applied to color images. But we can overcome these disadvantages by applying different distances and angles or different configurations to the parameters and combining them together into our features set and apply the machine learning to it. As we mentioned, we are getting a local binary pattern image. What about the features? We mentioned that we can involve other handcrafted features into our process, such as calculating GLCM features, GLRM or GLCM features from the local binary pattern. So GLCM computed from the original image will focus on the statistical features between pairs of pixels between the intensity values. On the other hand, if you applied it on the LPP, then you are emphasizing the local texture variations rather than the absolute pixel intensities, and this will make it less sensitive to illumination changes and noise. So here we are capturing spatial relationships based on the binary patterns instead of the intensity values. Again, you can combine the extracted features from here and here together in your feature set so that you can strengthen your feature set by extracting features based on the intensity values and binary patterns. After executing the code, these are the features for GLCM. These are the features from GLCM applied on the LPP. And if you check the different features, as you see here, the contrast increased from around 105 to around 9000. And that increase is amplified by the LPP, as it will enhance the texture discrimination. And also here for the similarity, it changes from 8 to 68, and also LPP increases heterogeneity, emphasizing the local differences, and the same for other features. Also, as we mentioned, we can combine all of these features together in your feature set to emphasize and strengthen it. As mentioned, local binary pattern, or the original local binary pattern, is subjected to noise, and it's one of its advantages. So different extensions and alternatives appear. One of them is called Uniform Local Binary Pattern, in short ULBP. And here we are considering only patterns that has at most 2 transitions, whether from 0 to 1 or 1 to 0 in your binary code. So here we are finding a pattern, and a pattern is considered uniform if it contains at most 2 bitwise transitions. So you may get no transitions, 1 transition, or 2 transitions at most. And here the uniform local binary pattern addresses the issue of high dimensionality of local binary pattern histograms by focusing only on patterns that accept uniformity. And here will make the histogram representation more compact and robust to noise. To do so, we created a new function called Uniform Local Binary Pattern 2D, accepts the same parameters. First, it calculates the local binary pattern matrix, and then creates another empty matrix to store the uniform local binary pattern. Then it loops on each element or each cell in that matrix, and it checks the number of transitions. How? Simply, it gets the current cell, converts into binary, counts the number of transitions, and the number of transitions is found by the change in the consecutive bits. So if it's 0 to 1 or 1 to 0, the number of transitions will increase, starting from 0 until you reach the maximum number of transitions in that LBB matrix. If at most 2 transitions is found, then the decimal value for the current pixel in the original LBB will be filled in the uniform matrix. So not all of the values in the LBB matrix will be filled here. Only the ones that has at most 2 transitions to be uniform. Finally, you apply normalizations and return the uniform matrix. Now go to script 30, local binary pattern extensions for 2D. We imported the necessary libraries, got the 2 images for the image and segmentation, got the ROIs and the cropped version, checked that it's not empty. Then we defined the parameters for the LBB computation, calculated the LBB matrix and LBB matrix uniform, both of them together, so that we can plot them alongside each other. We plotted a figure with 3 subplots, the original image, the LBB image, and the uniform one. When you execute the code, this will be the corresponding output at a distance 1, and this will be corresponding output at a distance 2. When you check both of them together, you may say that they are close together. But here, we are only considering the uniform patterns, so that when you are going to extract features, then you are going to extract features from the uniform patterns that has at most 2 transition points. As mentioned, we are addressing the issue of high dimensionality, and we are addressing the issue of noise in the uniform local binary pattern. So in this lecture, we have covered the meaning of local binary pattern and the beneficial points behind it. We illustrate the advantages and disadvantages of it and different extensions of the uniform local binary pattern. Also, we discussed how to calculate the kernel, which is essential part in calculating the local binary pattern matrix. Then we went through the different steps to calculate the local binary pattern matrix. Then we emphasized the importance of changing the distances and angles, and also the direction, whether it's called counterclockwise or clockwise. Also, we highlighted that we can extract features such as GLCM, first order features, and so on from the LBB matrix and the original matrix, and combine them together into our feature set, or we can apply the machine learning on each of them individually and compare the performance of each.